Okay, so yeah, it's all perfect. Let's start. So welcome all to live session 6. I'm audible, right? Am I audible? Hello?
Yes, sir.
Yeah, okay. So in today's session, yeah, thank you. So in today's session, what we will do, so the contents for today's session will be one is one is heat flow analysis a little bit, heat flow analysis in welding. So how the temperature will evolve with time, uh, based on time and position. What will be the temperature? What will be the effect of different process parameters on your temperatures? So those aspects we will go through once again. Next, we will maybe initially we will go through two more welding techniques which are solid state in nature. So I'm following the same contents what have been covered in your earlier lecture video, right? So we have solid state welding techniques. So what have been covered in those solid state welding techniques? So previously we had talked about this ultrasonic welding, friction stir welding, these things, right? Today we will talk about.
No voice is coming. You are not audible.
I am not audible. Am I audible or not? Hello,
Yes, sir.
I am audible.
Yes, sir. You are audible.
Okay. Is there any problem from your side, Notan? I'm not sure. Am I audible now, Notan?
Actually, you are not audible to me. I am checking from my side, and please, can you ensure from other participant?
Yes, they are saying that I am audible. Okay, please check from your side. So, yeah, we will continue. So, we'll talk about explosive welding and briefly we will talk about something called magnetic pulse welding. So, I'll very briefly discuss on these two different welding techniques, their process mechanisms, advantages, limitations, these things. And finally, we will finally talk about some hardening mechanisms. So what we will cover in hardening mechanisms. So basically, this is this will be much more on metallurgical aspect. So hardening mechanism will be very important to understand what is going on in terms of metallurgy in your fusion zone or heat affected zone or partially melted zone, different regions of welding, right? So in general, two different hardening we will talk about. So one is, I am sure that at least strain hardening you must have heard of, strain hardening or work hardening. These hardening mechanisms will be there for heat affected zone, right? So we are talking about hardening mechanisms in heat affected region of your weld region, and we will talk about precipitation hardening, right? So these will be in short our today's contents. I have checked from my side. Uh, can you rejoin, Nutan? I think that will be a better thing because other participants can hear me out, right? You just leave the session and rejoin again. I believe that that will serve your purpose. Ah, I need to message him. So, yeah. So first we will talk about explosive welding. So in explosive welding is typically used to bond some flat surfaces, right? So some flat surface of widely different metals. Now I am audible.
Yes, sir. Now you are audible.
Great, great. Okay.
Thanks. Thank you.
Yeah. So yeah, as I was talking, explosive welding typically used to bond flat surfaces, not any kind of some other geometries or any other complex geometries. Typically, it is used for flat surfaces, and mostly will prefer explosive welding because of its solid state nature and when you want to join some dissimilar metal, right? So let's say you want to join aluminum copper, or you want to join aluminum magnesium, or you want to join copper iron. So mostly for whenever there will be dissimilar material will be involved, and whenever you want to join large area, so if it is a flat surface, mostly it will be a flat surface, mm, explosive welding will be involved with a large area of joining. So one is dissimilar metal. So dissimilar metal in the sense there will be wide variety of thermophysical properties, right? So it will have different elastic modulus, it will have different plastic property, it will have different thermal conductivity, specific heat. Every property will be different. So thermophysical properties will be different. At that point of time, you can choose explosive welding as a technique to go for. Next one, when you want to join it through explosive welding, if large area of joining is involved. Okay. Now over here, let me draw a schematic. So over here, what you will have the components, you will have some kind of anvil. We call it anvil. Then you will have over the anvil, you will have the plates to be joined, right? So you'll have some contact angle. You'll have some contact angle. So this contact angle will matter, right? Ultimately, this will have some velocity through which it will impact this plate. Let's say this is copper and this is aluminum. So I will provide some impact velocity in the copper. So it will gain some kinetic energy because of this detonation and those things. So it will have some contact angle. So this is a process parameter. And over here, this is the explosive. I think I should use different color. So these are my plates to be joined. And let's say this is the direction of the detonation, right? So over here, the bottom sheet or the plate is positioned on your, this is rigid in nature, right? This will have no deformation as such. So this must be rigid. And the top sheet is inclined to this plate, inclined to the base plate or bottom plate, right? Now, the explosive material that is kept usually in the form of a sheet, which will be placed on the top of the two layers of metal, and that is detonated in a progressive fashion. So this explosive is detonated in a progressive fashion. So it will have some direction, like the way you do, you will have some welding velocity, it will have some direction of detonation, right? So because of detonation, what will happen? There will be a compressive stress wave will be getting generated. So I will create a compressive stress. What will be the order of that stress? It will be of some thousand of megapascal. So this much of stress will get generated because of that detonation. You can imagine how much kinetic energy will be generated, right? And then it will sweep across the surface of the plates. And because the impact is very fast or very quick, the strain rate will be very high over here. Do you remember I once talked about that your real stress of a material is a function of what? It is a function of strain. So in plastic property, you must have gone through this kinematic hardening, linear hardening, isotropic hardening, these things. So it must be a function of strain rate, and temperature, right? So over this these kind of welding techniques where there is lot of energy included, lot of impact energy is there, kinetic energy is there, everything will happen in at a sudden. right? So strain rate will be very high over here, and so whatever will be getting generated will be there at the surface only. So it will not affect the bulk of the material. It will only affect the surface. So I will I will write down that. So surface, I would say surface films. Surface films are liquefied. So there will be some local melt formation only selectively at the interface. Okay. Any question till now? Any question in terms of the mechanism of whatever I just talked?
No, sir.
So basically, this is a low temperature world, but also there will be a local melting because of high strain rate. Okay. And bond strength will be quite high, right? Yeah, bond strength will be quite high. Can you come across any kind of common application where explosive welding should be used? So I was talking about this copper to aluminum, aluminum to magnesium, copper to iron. When do you want to have some dissimilar metal combination? So a common application can be if you want to clad some kind of, let's say, corrosion resistant metal to a heavier base metal. So the cladding have been aluminum or titanium or copper or ASS, and the substrate will always be rigid in nature. So otherwise, it will not provide the sufficient amount of load, right? If it is a soft metal, uh, I just for some abbreviation, I was just talking about aluminum. Let's say if it is aluminum, can it provide sufficient load when it when copper is uh, applying this kinetic energy to aluminum? It will splash out because of softness of aluminum, right? So over which the metal is getting cladded. So let's say if this is ASS and you want to clad aluminum over here, this must be rigid enough to provide sufficient load, isn't it? Okay. Now, I will talk about little bit on some terminologies what is used in explosive welding. So I will talk about terminologies in explosive welding. Terminologies in the sense, uh, what are there in explosive welding basically? You'll have a base plate, right? One is your base plate. So what purpose it does serve? So base plate is basically I was talking about the anvil, right? This is kept stationary, and let's say this is the one on which I want to perform the cladding thing. So it could be the anvil, it could not be. So you can also place some hard metals over the anvil also, but they should be rigid enough, right? Then you have this flyer plate. What is flyer plate? So flyer plate is the one which is placed over your base plate, and during collision this flyer plate will hit onto the base plate, right? So from this figure, copper will be my flyer plate, right? I'm providing kinetic energy to copper. Now the selection of flyer plate and base plate is done on the basis of what? On the basis of mass per unit area. Whatever is less, so these two are chosen based on mass per unit area. So which one should be placed above? Its mass per unit area should be less or high? So I was talking about this must be rigid, right? So the density should be much higher for base plate compared to the flyer plate. So mass per unit area for the flyer plate will be less. Then you will have stand-up distance. What is stand-up distance? This is the one which maintains the distance between flyer plate and the base plate. As simple as that. So stand-up distance will help you in terms of uh, this distance helps the flyer plate to accelerate and acquire the required impact velocity to generate some kind of impingement, of course, right? So over here, so I will draw over here only. So this is my flyer plate. This is my base plate. So this distance will be the SOD, stand-up distance. Apart from this impact velocity thing, what else does it provide? It also provides the exit path of the uh, if there is any splash, or it also provides the exit path of the if there is any air formation between the flyer and base plate during the collision. That is secondary, of course, but yes, that is also an aspect of the joining mechanism. Then you have something called buffer sheet. What it does, or where it is placed. So buffer sheet is placed over your flyer plate. Buffer sheet is placed over flyer plate. What material it is made of? It can be made of some soft or damping material like rubber or PVC, this kind of materials. So what is the main role of this sheet? Main role is to protect the flyer plate from damage if it is happening. It may happen, right, during the collision due to some explosion effect. So the protection is the main purpose to provide this buffer sheet. And then you can have this explosive box, detonator. Those are there. So two main thing two main parameters are important over here. One is stand-up distance. I forgot about to tell about the angle. So I had talked about this contact angle. Is this contact angle also? Okay. Any question? Hmm.
No, sir.
No, understood, right?
Yes, sir.
Great. So next, we'll briefly talk about this magnetic pulse welding. So we'll just go through the technical little bit, what is happening over there. This is also a solid state welding, right? But in terms of mechanism, how? Yeah.
Survey, by which the workpiece is hold at an angle.
I'm not getting you. Can you come again?
By which thing the workpiece is hold at an angle.
Why the workpiece is kept at an angle?
मतलब by which thing मतलब किसकी हेल्प से होल्ड
किसके help
किया
से?
जाता है.
Uh, Possibly there could be some fixturing thing. So it is kind of, I would say, mm, this can be a beam kind of thing. So can you think of it as a beam where this is a supported over here? So this is fixed over here. Let's say this is fixed over here, or you are holding it with hand and you are applying a force over here. So this will create a bending moment kind of thing. So let's say you are thinking of in terms of strength of materials. So there must be some fixturing at this region. If it is fixed with some fixture, these must be free so that it will gain some kinetic energy. I'm not sure what should I. So as of now, I can say there must be some fixturing to fix this over there. I'm not sure what does it call. Okay.
Okay, sir.
So we are talking about magnetic pulse welding. This is also a solid state welding process. Now, through which mechanism it will create some force. The principle is same whatever we have seen in the explosive welding. In explosive welding, you are using some detonator to provide that force, to provide that sufficient force to gain that kinetic energy. Over here, you will generate a electromagnetic force, right? So typically, there is no need to apply any external heat, or there is no need to provide any filler metals. This is a solid state welding, right? Now the process involves, what the process involves, there will be a rapid discharge of a high current electrical pulse. So there will be some capacitor bank which will store huge energy that will discharge very rapidly, so that there will be creating a strong magnetic field. Now, if it is creating a strong magnetic field, it will induce what? Eddy current, right? It will induce eddy current in your material to be welded. Now, what are the key features, or what are the, I would say, what are advantages of these kind of solid state welding techniques? Let us write it down. So I will just put some notes. So heat affected zone will be very less, of course. These processes are very fast in nature because strain rate is very high. Capability to join dissimilar metals. No consumables, right? You don't need any filler metal or external heat, right? So over here, your workpiece will be positioned uh, near some magnetic coil or actuator through which you can generate some pulses. So I was talking about this capacitor bank, which will be discharging a high current pulse into your coil and it will create that magnetic field, right? And the opposing magnetic field will create a repulsive force that will uh, drive one of the workpiece at high speed towards the other. So because of high magnetic field, opposing magnetic field will create huge repulsive force to drive the workpiece at a high speed. This is my main mechanism of your magnetic pulse. Is there any limitations for magnetic pulse or even explosive? Let's stick to magnetic pulse as of now. Yes, there is limitation also by the name, as you can understand. So the process works based with conductive and non-magnetic materials, right? Such as aluminum, copper, and certain alloys. So if you want to join magnetic materials like steel, that can be more challenging to weld due to their magnetic properties, which can interfere with the electromagnetic force, right? There can be some thickness constants also. So this is most effective for relatively thin materials because if the thickness of the metal increases, effectiveness will get decreased because the magnetic field may not penetrate deeply enough to create the necessary force for welding. So there will be thickness limitation. Best suited for conductive non-magnetic materials. Of course, the cost will be very high, and the joint geometry. You cannot join some complicated geometry over here. So mostly it is effective for joining materials with simple, flat, cylindrical kind of geometries. So I would say flat, cylindrical geometries are best suited. What about the energy consumption? You need high power requirement over here, right? So it requires significant amount of electrical energy. to generate your high current pulse necessary for welding. Okay, so these were most on your welding techniques. So we will go through the questions once from whatever have been covered till now. Then I will move to this heat flow analysis. Heat flow analysis in the sense we'll just see uh, at different locations of your weld joints how your temperature will look like. Okay, can you quickly answer me for question one? There is something on this solid state welding technique, of course. These are very simple questions, anyhow. There is no need to think.
C.
So for me, for question one, C is correct. Anybody have any confusion? No, right? There should not be any confusion. Next, solid state joining process is used for large area cladding. This is also explosive. So at the very first moment I have talked about this, this is beneficial for large area cladding. Next, this I will come later because this is something on this heat flow part. Question 4.
Buffer layer.
Buffer layer is correct. Everyone agreed?
Yes, sir.
Yeah. Okay. Standoff distance in impact welding is normally kept at
A option.
which one?
A option. A.
Okay,
A.
right. This I will come later. This will come later. Yeah. Now I will. Now I will. So let me rub this off. Now we will be talking about analysis of heat flow. Let me draw. Let me draw something. Let's say this is your top view of your plate. This is my center line. Do you know what is thermocouple?
Sir, used to measure the temperature between 2
Measure
points.
temperature. Perfect. So this is used to measure temperature. So let's say I have connected one thermocouple in the center location. I have connected one thermocouple, let's say at 5 mm away from the center. Another thermocouple is 10 mm away from the center. And my heat source is the center line. So let's say I have created some flame. I'm doing some flame heating and I am moving the nozzle at certain welding speed, let's say VMM per second. Now, how the temperature will look like? So except for the initial and final transients of welding, heat flow in a workpiece will be, means if the length of your workpiece is sufficient in nature, means the length should be sufficiently large enough. At each point of your center line, it will feel some steadiness. So each point of this center line will feel same peak temperature. So let's say this is point 1, this is point 2, and this is point 3. If this is my temperature for point 1, after certain point of time, the same peak temperature will be felt by point 2. After certain point of time, same peak temperature will be felt by point 3. So if you somehow can join this peak temperature, let's say I have joined this peak temperature. This will come to a steady state. This is simply because of Fourier's law of conduction. What does it tell about? Whatever heat is coming in or whatever heat is getting generated,
Sir, heat is time independent. This graph tells.
so I am talking about at different locations of temperature. So if you are talking about a specific location, this is time dependent. Now, if you are thinking of as a whole, after certain point of time, this will come to a steady state. So in other words, we can say that let's say you are an observer and you are seeing that the nozzle is moving, and the observer is also moving with the heat source. Okay, so the temperature distribution and the pool geometry, that will not change with time. So if I am an observer and I am seeing, I am having same speed, temperature distribution and pool shape. So in terms of pool shape, I am talking about, not sure you are familiar with something called contour. So my pool shape will look something like elliptical. Okay, from the top view, this is something like this. The shape also will not change with time if you are an observer and you are moving with your heat source. Pool shape will not, right? This I am talking about the center line. But when you are going further away from your center line, what will happen to the temperature? So let's say this was my weld metal. This is my point 1, this is my point 2, which is away from the center point. This is point 3. Okay. Now, if my heating source is the center line, can you please mute yourself if you do not have any question? Yeah. So, if your heating source is in the center line, which point will experience the maximum temperature? If I am heating through the center, which point will experience the maximum temperature?
Point one, sir.
Point 1. Right, right. So, let's say this is something like this. There will be sudden heating. So, shoot up. The temperature will shoot up. And at certain point of time, let's say this is T1. We also call it soaking time. So, let's say this is temperature T1. My soaking time above this temperature will be this much of time, T, right? So this is one parameter. Now this is T1. What will happen to point 2? This will be the next peak temperature. But if you see, there will be certain lag there will be certain lag when it will achieve the peak temperature, and also the temperature will be little less, and also there will be change in the cooling rate. Next, something like this. So this is T2 and this is T3. So T1 is greater than T2 is greater than T3, but in terms of time is less. Am I correct?
Sir, can you explain this concept, this graphical concept, in briefly again?
I should explain this in what?
The oval shape and this graph and this rectangular portion. Can you explain this again
Yeah,
briefly?
yeah, yeah. So I was talking about, uh, let's say this was my, uh, I'm heating it with a gas flame, okay? And I am heating with a gas flame, which I am moving through the center of the workpiece. So this is the center of my workpiece, this black line. And I have put one thermocouple at the center. I have put another thermocouple at, let's say, 5 mm away from the center. I have put another thermocouple at 10 mm away from the center. Now over here I was talking about, so you know that in what happened? You just left. Okay. So I was talking about that, if you are hitting it up in the center will experience the maximum temperature. The next peak temperature will be for 0.2 and the next peak will be for 0.3. So this is for 0.1, this is for 0.2, this is for 0.3. There must not be any confusion. This is clear, right? Now, let's talk about effect of welding parameters. How will affect my temperature? Effect of welding parameters. So initially I will be talking about, let's say, what will be the effect of parameter on your pool shape. So in terms of pool shape, so what are the parameters? One is heat input, Q, another is welding speed. These are my two process parameters. Now if you see, if both these Q and V increases, your weld pool become more elongated in nature. So it will something look like this. So let's say uh, this is some 30 ampere, 7 volt. These are, I am providing some absurd values, and this is at 0.4 mm per second. Now if you increase your ampere and voltage, let's say you are going to 70 amp, 8 volt, you are increasing your welding speed also, you will see that your pool shape has been elongated, something like this. If you increase it further, it will be much more elongated. So you can see that the spread, the width, I will talk about melt pool width, melt pool width, melt pool length. More you go towards high ampere, high voltage, high speed, your length is getting higher, but this spread is getting narrower, right? Now this effect of welding parameters on your pool shape will be more significant on some uh, low conductive metals. Let's say there are two metals, aluminum and SS. Which one is having higher thermal conductivity? Which one is having higher thermal conductivity? Aluminium is having higher thermal conductivity compared to SS, stainless steel, right? Now this low conductivity of SS, because of its lower thermal conductivity, what will happen? It will be more difficult for the weld pool to dissipate heat and solidify, right? So these effects, you can visually see these kind of effects very clearly for these low thermally conductive metals. Will be more effective for change in pool shape. What next? What else do we have? We have cooling rate. We have temperature gradient. These are very important two process parameters which will affect your weld quality. Now, can you tell me? I possibly in my previous lectures had talked about something called heat input per unit length. What is heat input per unit length? So in an arc welding process, what is heat input per unit length? What is heat input? Heat input is basically the power what is getting into. Power is V into I. That is my total heat flux that will be getting generated. Now heat input per unit length is the ratio of your power and welding speed. So this is in joule per second. This will be, let's say, in meter or millimeter per second, whatever unit you are familiar with. So this will be finally come into per length of how much energy your welding technique is consuming, right? Now, how this heat input per unit length will affect your cooling rate and temperature gradient. So from experiments, it has been shown that if you increase the ratio of heat input per unit length, that is, sorry, this is not E. This is voltage into I. I is current, and this is welding speed. This is better. Now, if this ratio is increased, it has been seen from the experiments that what will happen? My cooling rate will be decreased. If you do some kind of preheating also, let's say you are doing some preheating of the metal, then also your cooling rate will get decreased. Can you tell me fundamentally, not go into the mathematical aspect, why because of preheating my cooling rate is getting decreased? Any guess? Cooling rate will depend on what? Cooling rate will depend on my temperature gradient, right? If your temperature gradient, yes, heat transfer, exactly, right. So heat transfer or heat conduction. So if your temperature gradient is much higher, your cooling rate will be much higher. Now, if you are doing preheating for a metal, so initially, uh, let's say this is no preheating and this is preheating. Now, if you are doing preheating, you are affecting more area of your metal to be heated up, right? So, if you are seeing the contour, if you are seeing the contour, there will be near uniform distribution of the temperatures if you are doing preheating. If there is no preheating, so initially it will be at ambient and then you are going to certain temperature, it will be not uniform. So the conduction of heat from the center or the dissipation, the time will be very high to uh, cool down, or the dissipation will be slow if you are doing preheating, because temperature gradient will not be that much high. What will happen for a no preheating case? Dissipation will be slow. Question? Yeah. Uh, you can unmute yourself.
Sir, I want to ask two questions. My first question is this: in fusion welding, precipit- precipitation hardened metal system in heat affected zone are affected by which of this: melting, coarsening, refinement, and transformation to hard precipitate?
So I am still not have gone to this precipitation hardening. Uh, is this a question from you? Means is this a multiple choice question from you?
You can explain the phenomena behind this, physics behind this, if you
Yeah,
know.
I will talk about precipitation hardening a little bit later. So I will cover it up once I finish this heat transfer part. I'll
Oh,
come to that. No problem.
okay, sir. And one more thing, you can also discuss about the transformation hardened metals like steel. Can you discuss?
Transformation hardening.
Yes, transformation hardened metals like steel.
Uh,
How we can increase the hardness of these types of metal?
so yes, actually this question is a little out of scope, but fine. Means for yeah, precipitation hardening I will talk about. I'll also talk about this work hardening thing,
Yeah.
uh, because of fold deformation and that thing. Now in steel, yes, transformation hardening is a more general term which is used for something called martensitic hardening. So yeah, yeah. So let me tell this in this way. So what I would say, so this is kind of a heat treatment process, right? Which is you have also talked about. This is also used to increase your hardness and strength of your steel material. Now over here there is something called austenization. The remaining of you, are you familiar with these terms?
Yes, sir. It is the part of heat treatment.
Yes. So this is a little bit out of scope from this discussion, but anyhow. So there is something called austenization. So what is happening in austenization? You begin by heating the steel to a temperature above its upper critical point, which is somewhere around, I forgot exactly. This must be somewhere around 700 for plain carbon steel. It You can check once. So this is called critical temperature. So critical temperature above 700 degrees C, but the steel structure will change uh, from ferrite or pearlite to austenite. So austenite is basically a FCC crystal structure, right? So austenite is a FCC crystal structure. So what does it do? FCC crystal structure, it can dissolve more carbon. Because it can dissolve more carbon, it will make your steel more hardened. Okay. So whenever you do this austenization or this heat treatment, the steel structure will change initially from ferrite or pearlite to austenite. Then you do quenching. What do you do in quenching? You rapidly cool your steel material using some medium. It can be air quenching, it can be water quenching, it can be well quenching. So some kind of quenching you do. So rapid cooling transforms your austenite into martensite. So austenite.
Sir,
Yeah.
sorry to interrupt you.
Mhm.
I am saying that among melting, coarsening, refinement, and transformation to hard precipitates, which one of these will affect the precipitation hardened metal system in heat affected zone during fusion welding? Among four: melting, coarsening, refinement, transformation to hard precipitate. Among
Acha,
these,
acha, 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 acha. Okay, okay.
among
So
these
this
four,
was a question from your side. So there were
yes,
four options, right?
yes, melting,
Uh,
coarsening, refinement, transformation to hard precipitate. Melting,
so
coarsening,
I would say in heat affected zone, right? Is this
yes,
heat
yes,
affected zone or fusion zone?
in heat affected zone.
So in heat affected zone, both refinement and uh, hard precipitate formation. It depends on what material you are doing. So precipitation hardening is mm, more observed in some alloys of aluminum, copper, Si alloys. So precipitation hardening is suitable for these kind of alloys.
Yes,
So both precipitation hardening and work hardening or this refinement, recrystallization thing, both are observed in heat affected zone. I would
but
come to that. I would come to that.
sir, in coarsening, the hardness will be, I think, affected.
It will
In
get
heat.
deteriorated. So
I
if
am
you
not,
are
I am not sure. That is why I am also confused in this question. That is why I have asked to you.
so
Uh,
coarsening will deteriorate your hardness or strength property.
yes,
Because there is something called Hall pitch relation. I'm not sure you have heard of not, but yes. So Hall pitch relation will talk about relation between your yield strength, which is a function of grain size. So let's say D is my grain size.
yeah,
Okay.
okay,
So uh, if you are have a refined microstructure, if you are have a fine grain structure, let's say you are having some structure like this, and you are having some structure like this, very refined. So there is some factor called surface area to volume ratio. So more refinement, there will be this ratio will get increased. My surface area to volume ratio will get increased. And because the surface area to volume ratio is getting increased, it can sustain more load. It will harden more compared to if its surface area to volume ratio is less. So always refined microstructure will give you much more strength. So if there is coarsening happening, the hardness must get deteriorated.
Ye- So, sir, can you tell me the most appropriate answer among four: melting, coarsening, refinement, and transformation to hard precipitate? Which one will affect the which one will be affect the uh, which one will be the affect the precipitation hardened metal system?
Huh. So there is already it is talked about precipitation hardened system. So there must not be any confusion then.
So,
So for precipitation hardened system, it must be hard precipitate hardening.
which one will be the correct answer?
The last
Melting,
one.
coarsening, refinement, and transformation to hard precipitate.
Precipitates, yes. The last one.
Last one. Okay.
Yes.
Okay. And the reason for the increasing in hardness of transformation hardened metals like steel in the heat affected zone. Refinement of precipitates, recrystallization and grain growth, dissolution of precipitates, formation of hard faces.
Can you come again this question?
The reason for the increasing in hardness of transformation hardened metals like steel in the heat affected zone. The first one is refinement of precipitate. Second is recrystallization and grain growth. Third is dissolution of precipitates. And fourth is formation of hard faces.
Formation of
Hard faces.
hard
Phases.
phases. Yeah, the last
Yeah.
one then.
Last one.
Yes. So because you are talking about transformation hardening, it is most on your metallurgical phase formation. Transformation hardening is what? You are changing the structural aspect. You are going from ferrite pearlite to austenite. You are going from austenite to martensite. You are changing the phase of your structure. Crystal structure will be changed. So from FCC structure, it will be somewhere it will go to some BCT crystal structure. Uh, so yes, the last one.
Okay. Thank you.
Yeah, welcome. So I was talking about yeah preheating thing. Okay, we don't have time much. So question 3, question 4, question 5. I will come to the recrystallization a little bit later. Huh. So can you quickly answer for question 3? Which one is the correct one? It says distance from fusion weld zone increases, peak temperature, heating rate, and cooling rate will what increase, decrease, and what will be the effect on your cooling rate? Sorry, heating, cooling rate, and the peak temperature. Hmm?
I think B is the correct answer. I think so.
B.
Yes, sir.
I think, sir, A is the
Yes.
correct answer.
A should be the correct answer. I'm talking about if you are going away from your fusion zone. So the maximum temperature will be there at the fusion zone. If you are going away from the fusion zone, my peak temperature, heating rate. So see this, where is that graph?
This.
This graph. See this graph. If you are going away from the heating zone, so the point 1 was my heating zone. That will provide me the maximum temperature. If you are going further away from your heating zone, your peak temperature, your heating rate, your cooling rate, all will get decreased. Okay. Okay. What was that question? Question 3, right? And question 4 we have done, 5 done, 6 remaining, 7, 8. Okay. Next we will go to this work hardening part. Okay. So we'll move to something called work hardening. So as you are talking about, there are several ways through which you can do this hardening thing. There can be solution hardening, there is work hardening, precipitation hardening, transformation hardening. So as of now, we'll talk about two things: work and precipitation in your heat affected zone. Precipitation. But yes, I also was talking about transformation hardening a little bit. So that is mostly for steel material. Now, yeah, yeah. So in work hardening, what we will go through is something called recrystallization. Okay, what is happening in recrystallization? If you see, most of the energy expanded in work hardening process, uh, that appears in the form of heat, right? So a finite fraction is stored in the material as a strain energy. Okay, so when you will anneal a work hardened material, what will happen? The deformed grains in that material will tend to recrystallize by forming some fresh strain free grains, right? So recrystallized grains will always be strain free, right? Those will be soft in nature, just like the grains that have not been deformed. So what is the driving force for recrystallization? So the driving force is the stored energy or the strain energy, what is happening because of the deformation process. Now the extent of recrystallization, what will happen if you are, let's say you are increasing your annealing temperature, your recrystallization volume will increase or decrease? If you are increasing your annealing temperature, the possibility of recrystallization will increase or decrease? Hmm? Recrystallization increases if you are increasing your temperature.
Yes, sir. Extent of recrystallization increases with the temperature and time.
Right, right. So it is expected that your strength or hardness of your work material will tend to decrease with increase in temperature and time as you suggested. Exact. In fact, um, before recrystallization takes place, there is something called, what happens before recrystallization? There is something called recovery. Okay. So before recrystallization takes place, there exists a period of time during which certain properties of your work hardened material, uh, for instance, let's say electrical conductivity, right? So certain properties will tend to recover without causing any microstructural change. This phenomena is called recovery. So before, I would note it down. Before recrystallization, certain properties will tend to recover without causing the microstructural change, right? Then after recrystallization, there is something called grain growth. So upon completion of recrystallization, grains begin to grow. What is the driving force when grain growth is happening? So the driving force for
Surface
recrystallization is,
energy.
sorry,
Surface energy.
yes, great. So surface energy is the driving force when the grain growth is happening, right? So what will happen? So the total grain boundary area or the total surface energy of the system will be reduced if there is coarse grain or fine grain. Let's say you
Sir,
have,
sir, the extent of grain growth increases with temperature and time. What are you saying?
yes, of course, after recrystallization, if you are providing same temperature and you are allowing it more time at that certain temperature, then
Yes.
grains will grow, it will
Oh,
get coarsened,
yes.
right? So I was talking about that, the total grain boundary area. So this I am making some abbreviation. Huh? This is a grain boundary area and total AC surface energy. These will be reduced whenever there will be coarser grains present or during the progression with grain growth. Okay. Okay. Now, yeah. Now, in terms of thermal cycle, so we are talking about this temperature distribution, right? So closer to your fusion boundary or closer to your fusion region, higher will be the peak temperature, right? I mean, uh, of course, at the center, the temperature will be highest. Let's say this is region 2. This will be at much higher temperature compared to region 3 and region 4. This is correct, right? So
Yes,
over
sir.
those regions in the heat affected zone, the material will stay above some effective recrystallization temperature for more time, right? So let's say this is my heat affected zone if this is 1, this is 2, this is 3, and this is 4. So over here, the possibility of happening recrystallization will be much more, along with grain coarsening. So it possibly recrystallization with grain coarsening. At point 3, there will be recrystallization without grain coarsening. So those will be much more defined without grain coarsening. Please remember these abbreviations. And the point 4 will be there will be no recrystallization, or that will be much more towards the base metal microstructure. Right? So what is happening? The strength of your work hardened metal decreases with increase annealing temperature I was talking. Right? So as you approach your fusion boundary, the strength and hardness of your heat effector zone will get decreased. Correct, no? Ah, hi Shurya. Okay. So now this will also affect the size of your heat effector zone. So both size of heat effector zone and the retention time above which the effective recrystallization temperature is there, that will increase with your increase in heat input per unit length. So if I increase my heat input per unit length, everything is interconnected. If I increase my heat input per unit length, my heat affected zone size will get increased. The time for which this is staying at above recrystallization temperature, that will get increased, right? So those aspects are there. And can you tell me, let's say there are two processes. One is electron beam welding and one is gas tungsten arc welding. Now, which one will have tendency to create more recrystallized grains based on the discussion, whatever we have done?
GTAW.
EBW will have what? EBW will have low heat input and high cooling rate. Compared to gas tungsten arc welding. Because of that, the temperature for which it will stay at or above the recrystallization temperature will be very less. Okay, so it is observed in heat affected zone for your EBW metals that the recrystallization will be very less. The tendency or possibility of happening recrystallization will be less in EBW compared to gas tungsten arc welding. From this concept, heat input per unit length.
Yes, high energy density in
Right.
EW.
In
Yeah.
EBW.
Yes,
Right.
yes.
Right. Okay. So do we have any question from strain hardening? Let's say. Let's check. Yeah. So most metals are decrystallization temperature in terms of melting temperature about which one is true? Which one is true?
C.
C. C is correct. I will come to this part Excess solute. Anyway, if you know, you can tell me the answer. Excess solute present in the matrix above solubility limit. So this is something on precipitation hardening. This is called supersaturation. Ah, okay. Uh, leads to supersaturated solution. I have posed the question in a wrong way, but yeah. So if there is excess solute present in your matrix, I will come to this precipitation hardening portion quickly. So this is called supersaturated solution. This question we skipped. As per Weld thermal cycle of a location, what will happen if you are increasing your thickness of base metal during fusion welding?
सर इंक्रीज इन थिकनेस पीक टेम्परेचर रिड्यूस होता है और सोकिंग टाइम भी रिड्यूस और टाइम टू रीच पीक टेम्परेचर हाई इंक्रीजेस
So peak temperature will decrease basically.
यस बट टाइम टू रीच पीक टेम्परेचर इंक्रीजेस
That will also increase.
यस
But soaking time is different.
या
Soaking time is different. So let's not confuse with soaking time with time to reach at the peak temperature. So over for specifically for this question, yes, peak temperature will decrease. That is the correct one.
यस 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 यस
Because thickness is increasing, what is happening? The mass of the system is getting increased,
या
right? It can dissipate heat very quickly. Because it can dissipate heat, peak temperature will get decreased.
यस
Preheating. Preheating results in, this also I have talked about. Preheating results in
डिक्रीज कूलिंग रेट
decrease in cooling rate. And what about the last one? And then I will come to the precipitation hardening. Under the same heat input and welding speed, weld penetration. Uh, am I audible, right? I thought is my connection still there? Am I audible?
Yes, sir.
Thank you. Thank you. So under the same heat input and welding speed, my weld penetration will increase with increase in power density.
यस
Okay.
यस यस
So next we will go to briefly talk about we'll briefly talk about precipitation. Precipitation hardening. So I will take an example of aluminum copper alloy. Okay. So this is a typical example of precipitation hardening metal. Now, how should I start? How should I start? I would start from drawing some phase diagram. Okay. So let's think of, let's assume that I'm talking correct. So this is my wet percent of copper and this is temperature. You must have gone through mm, this phase diagram for iron carbon, right? This is somewhere same. So this will something look like this. So I have just stick to this eutectic part. I hope these terms are familiar. You are familiar with these terms, right? Eutectic. I had talked for eutectic in one of the classes. Now let's say these are 3 points. 1, 2, 3. This is complete liquid. So this is 0% copper, so pure aluminium. This will be alpha phase. This is liquid plus alpha, and there will be alpha plus theta actually. Theta is some phase for Al to C. Please stick to me. It may not be very you may not be very familiar with these terms. You may be. Now this alpha phase. What will happen to alpha phase? This is called solvus line. Okay. So I had talked about in my earlier lecture class. This is called solvus line. So what we'll see, solubility of copper in alpha phase will increase with increase in temperature. See, if you increase the temperature, the solubility of copper in alpha phase will get increased, right? Consider some alloy of aluminium and 4% copper. Okay, what do you do in step 1? In step 1, you initially solution heat treat. So you heat treat the alloy in the alpha phase temperature range until it becomes some solid solution. So I have made the solid solution by increasing the temperature at that temperature range. Then what I will do, I will quench it. What will happen upon quenching? It will rapidly cool. It will rapidly cool. The solid solution will rapidly
Rapidly cooled by water.
uh-huh. Yeah. You can cool it through water. Even for rapid quenching, air cooling. Yeah, sorry, oil quenching is much more effective. Okay. Now, what it will do? It will form some supersaturated solution. Supersaturated copper. It will create a supersaturated copper upon quenching. Next, in step 3, what we will do? You will do some aging. You can do artificial aging, you can do natural aging. What is aging? This allow the strengthening phase to precipitate from that supersaturated solution. So in artificial aging, you heat up the metal at certain temperature. It can be somewhere around 100 to 200. And if you are doing aging for more amount of time, it is called natural aging. That is also aging. So it will form something like this. So from the supersaturated solution, uh, there is something called GP zone. Then you will have theta double dash, theta dash, then you finally theta precipitates. So these are metastable in nature, and this is a stable precipitate. Now you see, can you tell me which atom is having smaller size, copper atom or aluminium atom? The atomic diameter of copper is much less than aluminium.
Yes, sir.
Okay, so you see in the GP zones, when they will be richer in copper than the solid solution, the concentration of copper will be much high in the supersaturated solid solution. The crystal lattice, what it will form, it will be strained around that GP zone. So the strain field that will be associated with the GP zone will be very high. Okay, so strain associated with zone is very high. What I should mention over here, what else I should mention over here, at least to remember, is the maximum hardness, the maximum strength when it will happen. What happened?
This, what, sir? I beg your pardon?
My screen got off.
Yes, yes.
Just wait. Please wait. Please wait, huh?
Okay.
Not sure what happened. My tab network is not working. Oh, yeah, yeah. Yes. Perfect. No internet.
आज रखी थी वो खा ले चलिए खिचड़ी खाना खड़ी है खाएगा आप खाए कौन जाएगी मच्छर गरम
Yeah, can you see it now?
Yes, yes, yes.
Yes, sir, visible.
Yeah, great. Okay, okay. So, what I was talking about? Maximum strength. Yeah, okay. So, I was talking about this. When we'll get maximum hardness or strength, right?
Maximum
So,
hardness is at GP2.
maximum hardness will be at GP2. Perfect, perfect. So, when the amount of this theta double dash precipitates, are you from metallurgy?
No, sir, no. No.
You're from mechanical.
Yes, yes.
Okay, good. So, typically, I have not seen people from metallurgy. Uh, You are in MTech, PhD, BTech.
Sir, presently I have completed my MTech.
Okay, you are completing your MTech,
Yes,
and you are working in.
I'm not working
You are
in.
working in which? You are working in which project area?
Okay, project area, sir. I have work on two project areas. First one is on MR fluid and second one is on linear friction welding.
Linear friction welding. Okay,
Yes,
okay.
yes. Have you heard about linear friction welding?
Yes. So I work in friction stir welding.
Okay,
Yeah.
okay. On which material you have done the work?
So I am working in copper aluminum dissimilar material.
Okay, okay.
Okay. So as you are telling that in GP2 region there will be the maximum hardness or strength. Also some contribution can be from that theta precipitate also. But yes. So if you see in terms of graphs, if you see in terms of graphs, uh, it will look something like this. So let's say this is aging time and this is hardness. What is the unit of hardness? What is unit of hardness? There is something called hardness number. So usually we talk about this HV. So this will look something like this. This will be my theta precipitate. This will be my theta dash precipitate. This will be GP1 region. Let's say this is aging at 190 degrees C. And if you are aging at some different temperature, this is GP2. This will something look like this. The precipitate theta precipitates are more stable. The hardness is the least compared to that theta double dash or theta dash precipitates. Okay, I think we should finish up over here.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. You can finish.
Yes, yes. Hello, hello.
Thank you.
Sir, can you share your contact number?
Yes, my contact number. Okay,
Yes, sir. If you are comfortable.
no problem. So this is my WhatsApp number also.
Wait, sir. I am going to note.
Anytime, anytime.
Sir, wait, sir. Wait. Thank you, sir. Now you can. Yes, thank you.
Bye bye.